Can you see my
Okay.
screen?
Yes, perfect. Yeah, now we are going to switch our gear a little bit to topology. So Michael, we're going to go algorithm for automatic decision making and topology. Yeah, Michael, please go ahead. Yeah.
Thank you very much. Thank you for organizing this conference. Thank you for inviting me to speak. There will be some topology, but in my view, topology and geometry are, well, very close to each other. So topology is also a geometry, so it's not out of the scope of this conference. So my talk will consist of 3 parts. So the first part, or part 0, will be an introduction, very general introduction. There will be no geometry or topology there, but a very general context. And then I will speak about robot motion planning and its complexity, and topology will play a role in this part. And then the second part, or the last part, will be about more recent work which we did with my collaborators, which is called parameterized motion planning. So let's first start with part 0. So I will consider the following question. Why do we care about automatic decision making? Do we need automatic decision making? What is decision making in general? So I will just list my questions first. We will see that there are essentially 2 types of decision making when you have discrete or continuous version. In the discrete case, you have choices out of finitely many possibilities. You make your decision making a choice out of finitely many possibilities. And there are other types of decision making when you make your choice, make your decision by selecting an option from an infinite set of choices. And I will discuss in my talk the structure of these algorithms which make automatically decisions. And we will see that they are unstable. They are not, they cannot be stable. And we will see how topology helps to understand the degree of instability of such algorithms. So let's just start with mentioning that in our generation, I mean, AI is a kind of major dream of our generation. AI is artificial intelligence, and understanding what is an AI is not an easy task. Vaguely, we can say that AI is the ability of machine or an algorithm to implement human tasks or to mimic human behavior. But is there a rigorous definition of what is AI? And I'm asking this question because I want to show, and I want to argue that AI is essentially about making decisions and making choice. Philosophical study of artificial intelligence, it goes back. In my view, it should be traced to the work of Bertrand Russell and then Ludwig Wittgenstein and Alan Turing, of course. The dates are shown on my slide, and Alan Turing is very well known as a father of modern computer science. He was also a philosopher, actually. He wrote an article in 1950. He published an article which has the title "Computing, Machinery, and Intelligence." And in this article, he asks the question, how to define a machine intelligence, or what we call now AI. And he said it's not possible to define it rigorously, because you cannot define what is a machine. He didn't want to define what is a machine. He said it is not right thing to do. But instead, he suggested a test. He said there is a test which he called imitation game. And this test is as follows. So there is a room. There are two rooms. In one room, there is some machine, which may be anything. And in the other room, there is a human. And on top of that, there is a kind of judge, human judge, human being who serves as a judge. And questions are being asked to both rooms, and the judge doesn't know where is a computer, where is a human. And if the judge cannot, well, only looking at the questions, if the judge cannot decide where, in which room is the computer and in which room is a human, this means that this computer passed the test, passed its imitation game. So in some sense, Turing says that functional, I mean, the computer must answer questions. If it answers questions the way the human would do, this means that it is intelligent. And this picture, you can see this from this very well-known movie, which is called Imitation Game. And this shows this computer which broke the code during the war. Okay. So according to this test, I mean, intelligence test, we need the computer or the machine must be able to answer questions or make choices. And choices may be like choices between finitely many options, like left or right, buy or sell, red or green, right? So these are quite important situations when computer, let's say, drives a car and a GPS decides left or right. And buy or sell, it's also quite an important issue on the stock market. But also there are situations when choice is not finitely many options for choice, but there are infinitely many options, continuum. And this is shown on this picture. So this robot must find a route from a trajectory from its current state to get to the desired state, and it must avoid the obstacles. So we can see on this picture that there are, well, continuum possibilities. And robot, if we want this robot to be autonomous, it must decide himself which way to go. And in my talk, I will mainly focus on the situations when you need to make a choice out of continuum, out of infinitely many possibilities. Well, I think I'll just skip this slide. So I just want to show you also this situation when you have many drones flying as one system. They are coordinated, they have to perform certain tasks, and they form one system. So they must have some sensing, understanding of what others do, and they should not collide with each other, which is an important thing. And in my talk, I will discuss questions of this type when you control many drones at the same time. So before I start specifically about my work and the work of my collaborators, I just want to mention that this field of algorithmic motion planning is a well-developed branch of modern robotics, and there are two very well-known monographs which are mentioned here. One is the book of Latombe, published in '91, and the second is a book of Steve Laval, which is more recent, published in 2006. Okay, so now we will just, I just want to say that like previous speakers, I don't want to try to present most recent and most technically kind of top results, but on the contrary, I want to present the main ideas of this approach and the nature of this theory and typical results which you can achieve here. So mathematically, if you model a system or a machine, you can always, well, typically you can assume that there are finitely many parameters of the system which determine its state. It may be some measurements, some angles, some distances. And if you put all these parameters in one vector, this will be a point in some Euclidean space. And you can say that the configuration space of the system is a subset of some Euclidean space of some large dimension Rn. And it has topology and it has actually metric. So it is a topological space. And points of this system are states of our system, points of the space are states of the system, and motions of the system correspond to continuous curves in the configuration space. So looking mathematically at what motion planning is, or what is controlling, what is a control of a system is, we can say that the system is just a topological space, and points are states of the system, and motions of the system are curves in the space. So this is an example, a robot arm, which is a very important mechanism. So here you can see robot arm with 4 bars. It can be, the configuration space is either torus of dimension 4, in case if it is planar, if this robot arm is planar. But if it is in 3 space and each bar can take any 2-dimensional angle, then it is a product of 4 2-dimensional spheres. And in fact, there are theorems, mathematical theorems, they're called universality theorems, which state that essentially any manifold can be realized as configuration space of some simple system. So now I start my part 1 of my talk, and it's called Robot Motion Planning and its Complexity. Okay, so I say let X be a path-connected topological space. As before, I mean, I understand it being the configuration space of my system. I will denote the closed interval 0, 1, and the symbol x to the I will denote the space of all continuous paths representing motions of the system. So a motion planning algorithm. So here, this is a very important for my talk, this definition. What is a motion planning algorithm? And maybe before this, I should say that if we want our system to move autonomously, it must have a motion planning algorithm. So it means that it must know how to move from any A to any B, from any state to any other state, um, once it's needed. So this is exactly provided by this algorithm. It is a computer program which is installed in this computer of this robot, and it describes this function which is called here A. It is a map from X cross X. So input are pairs of states of the system, and output of this algorithm is a motion of the system, and this motion must start at the first point and end at the second point. And this can be expressed using the language of topology, that the composition, this algorithm, and then this map P, which is described on my slide, composition of this A and P must be the identity map. And this P is a map which associates with every motion the pair of its initial and final points. So this condition actually means that the algorithm, this map A, must be a section of this map P, and actually this map P is a fibration, in the sense of Hurevich. So this is what I already said. This algorithm associates with every pair of states a motion which starts at A and ends at B. And then there is a lemma, which is important in this subject, and it says that a motion planning, a continuous section A exists if and only if X is constructible. And example, if we have a convex set and the configuration space is a convex domain, then we can just go from A to B along straight line, and this is continuous. This motion planning algorithm is continuous. So I just want to emphasize that continuity here means continuity with respect to the initial finite configurations, and not with respect to T. With respect to T, they are continuous anyway. Okay, so now this lemma can be rephrased in this form. That for a system with non-constructible configuration space, any motion planning algorithm is discontinuous. So discontinuous means that you can, if you have, you can find a pair of initial finite configurations A and B, such that sufficient. Actually, my picture is not very good. Sorry, my drawing is not very good. It's not correct actually. So point B prime must be a small perturbation of point B. Point A prime is a small perturbation of point A, but these motions they could be very different. Going from A to B will be very different from going from A prime to B prime. So this corollary is equivalent to that lemma from the previous slide. And here, there's an example when if you have again, convex island, but this island has a lake in the middle, then this robot, there is no continuous algorithm on the whole island. Any such algorithm will have a discontinuity, as I have shown you on the previous slide. Okay, so now we want to measure this discontinuity of such algorithms. I mean, they can be discontinuous, but can be discontinuous in different level discontinuity. There is a number which measures the level of, how to say, the severity of discontinuity. And this number is called topological complexity and is denoted by Tc of x. And it is defined as a minimal integer k, such that x cross x, the product x cross x, can be covered by k plus 1 open sets, u0, u1, uk, with the properties that there exists a continuous section Si over each ui of the pulse vibration P, which was described above. There is an equivalent definition of this TCX, and it is more convenient and this kind of obviously related to algorithms. This definition says that this number TCX can be defined as a minimal k integer, non-negative integer, such that there exists a partition. So now it is not a cover, it's just partition. And the sets F0, F1, Fk are arbitrary, with the only property we require that each of them admits a continuous section of this pulse vibration P. This TCX has the following important properties. First, it says that the first property states that TCX is a homotopy invariant of X, so it depends only on the homotopy type of X. And second, says that it is zero if and only if X is constructible. In fact, the second property is equivalent to that lemma, which we saw earlier. Okay, so let's look at examples. And the first example is, of course, the circle, kind of simplest, not constructible space. So for the circle, if we want to construct an algorithm of moving from A to B on the circle, we can define the first set F0 to be the set of pairs which are not antipodal. So if A and B are not antipodal, we can move from A to B along the shortest geodesic arc, and it will be continuous as function of the endpoints. And the remaining set, let's call it F1, it will be the set of pairs which are antipodal. And here we can define the algorithm of going from A to B as follows. We can just fix an orientation of the surface of the circle, fix some orientation, and then we move from A to B in the positive direction along this geodesic arc of length pi. So conclusion, the topological complexity of the circle is 1. Well, because we have a partition with 2 sets, and it cannot be 0 because the circle is not constructible. So it is 1. However, if you look at higher dimensions, spheres of higher dimensions, so we see similarly we can easily conclude that the topological complexity of any odd dimensional sphere is 1. And this is done similarly to this. Again, the set F0 will be the set of all not antipodal pairs, and the set of F1 will be the set of all antipodal pairs. The motion planning on F0 will be exactly as before. So if they're not antipodal, you move along shortest geodesic arc. And if they are antipodal, then what we do, we fix, now we use the fact that dimension of this sphere is odd. So we know that the sphere admits a tangent vector field, which is non-zero at every point, everywhere non-zero tangent vector field. So we can move from A to B along the geodesic arc, which starts, which has initial velocity vector given by this vector field at point A. And this shows that the topological complexity of any odd dimensional sphere is 1. However, we cannot do the same for even dimensional spheres because there is no such field, there is no tangent field on even dimensional sphere, which is any such field must vanish at least at one point. So what we can do, we can take this, such field which vanishes at exactly one point, and then what we described here, this strategy over F1 will fail at one point. At one point, we will not, for 1A, we will not know how to go from A to minus A. So this will be an extra set. This we will define F2. So it will be 3 sets, F0, F1, and F2. So this argument will show that the topological complexity of even dimensional sphere is less or equal than 2. However, it actually equals 2, and to show this, we need to use cohomology. We need to use cohomology. And so now I just want to mention this cohomological lower bound for TC. So we know that cohomology has a structure of an algebra. There is a product. And we look at tensor product of cohomology algebra to itself. And it has also a very well-known structure of graded algebra. And with the cup product, the map from tensor product of cohomology algebra to itself to the cohomology algebra is actually an algebra map, and its kernel is an ideal. So elements of this ideal are called zero divisors. And example of zero divisor is this element 1 tensor u minus u tensor 1. So it is a non-trivial element, non-trivial tensor, but if you apply cup product, it is 0. And more generally, there is this, for any two classes, u and v, u tensor v minus v tensor u with certain sign. This is a zero divisor. So this theorem, which gives lower bound for the TC, states that if there exists some number k zero divisors such that the product is non-zero, then TCX is k or higher, cannot be smaller than k. So if we use this theorem, we can easily show that TC of even dimensional sphere cannot be smaller than 2. So it is 2. Okay, so here are some examples for surfaces of different genus. And genus is, if genus is 0, it is a sphere, so TC equals 2. If G equals 1, so it's torus, TC equals 2 again. But if G equals 2 and higher, then topological complexity equals 4. And we see that it is actually double twice dimension. So actually we will see that generically TCX is twice dimension, but there are many situations when it is not, when it is smaller. I think I'll just skip this. Just mention this result about real projective spaces. So for when n is not 137, the topological complexity of RPN equals the smallest dimension k, such that RPN admits an immersion into Euclidean space of dimension k. And for n equals 137, TCRPN is just n. So this result shows that TC in general is complicated invariant because topology, algebraic topology, and differential topology accumulated many interesting results about immersions of real projective spaces. And here are some numbers, specific numbers, and you will see, I mean, they are quite irregular. There are certain sequences, infinite sequences of dimensions for which immersion dimension is known. However, there is no general formula for immersion dimension, and therefore there cannot be, we cannot expect a simple general formula for TCRPN. So this actually, what I told you now, is based on my first paper in 2003, and then on the paper with Sergei Tabachnikov and Sergei Uzvinsky about real projective spaces, which was published also in 2003. Okay, so now I start my part two, and so part one was kind of old, 20 years old results, and there are much more advanced results by now. So in this second part, I will tell you about more recent work which we did jointly with Daniel Cohen and Shmuel Weinberger, and it is about parameterized motion planning. So so let me explain what it means parameterized, and what is the difference between this ordinary motion planning, which I considered previously, to this parameterized. So we want our algorithms to be universal in the sense that they should be able to function in a variety of situations involving external conditions which are viewed as parameters and are part of the input of the algorithm. A typical situation of this kind arises when we are dealing with collision-free motion of many objects, robot, moving in the 3 space, avoiding a set of obstacles. So let's just imagine that just very special situation that we have some mines in some ocean, and we have many submarines, and these submarines should move from some initial position to some final position, avoiding these obstacles. So this is a typical situation when you have many objects and some number of obstacles, and we need to avoid them. However, these mines can be moved, I mean, from day to day. I mean, they can be movable. And if we have one algorithm created for one set of mines, it will not work for another set of mines. So what we want actually, we want to have an algorithm which works for arbitrary set of mines. So this algorithm which take positions of mines as input as well, together with the data about submarines and their desired positions. Now we want to formalize this mathematically, and we can do it as follows. So we have a map P from space E to B, which we will assume to be a fibration. So this space B is space which parameterizes external conditions. So a point of B will be viewed as external position, external condition, and the configuration space of our system, given those external conditions, is the preimage of this B, of this point B. So point EB, the fiber above this point B, is the configuration space of the system under the external conditions B. So we have the space E is a union of configuration spaces corresponding to different external conditions. And once we are given the external conditions and 2 points, E and E prime, lying in the fiber above the external conditions, so which are consistent with those external conditions, then we want to produce a curve, a movement of our system from the state E to the state E prime, which also lies in this fiber, which means that for every moment of t, this state gamma t is consistent with the external conditions B. So, well, I can denote by EIB the space of paths which lie in a single fiber. So each such path lies in a single fiber of this vibration, and the space E cross E over B is the space of pairs of configurations lying in the same fiber. So we have this map, capital Pi, which goes from EIB to E times B, E times E over B, which is given by this formula. So the same formula associates with gamma the pair of the initial and final configurations. And we can define parameterized we can define parameterized topological complexity, which is called here TC of this vibration P, as the sectional category of this map capital Pi. So it is sectional category is also known as Schwarz genus. It means that there's a minimal number. So this on this slide, TC of this vibration is the smallest integer n, such that the space E cross E over B admits an open cover with n plus 1 open sets, with the property that each set UI admits a continuous section of this vibration pi. And here is a main example, which actually was our main motivation for this work. So consider a system represented by n pairwise distinct objects, Z1, Zn. So we have n robots, which are represented by distinct points in Rd, and they have to move in the complement of m obstacles, O1, Om, in the space Rd. So we denote by FRDM the configuration space of obstacles, which is called B. So B is configuration space of M obstacles in Rd. And E will be the configuration space of N plus M distinct points in Rd, which are represented by N robots and M obstacles. So we have this vibration. Vibration associates to the configuration of robots and obstacles, only the configuration of obstacles. This is well known in topology as the Hadel-Novid fibration. So what we want is to compute, to find this topological complexity of this vibration, and this is actually exactly the complexity of the um, algorithm when you control many drones flying in space at the same time and in the presence of any number of obstacles which are also fly independently of drones. Um, so, well, I have to be careful about time, so I want to mention a few examples. So if the vibration is a trivial bundle, then this parameterized topological complexity is the same as the complexity of the fiber, complexity of X. So it is the usual invariant. The second example says that if we have a principal bundle with a group, connected topological group as a fiber, then this parameterized topological complexity is again the same as TC of the fiber, and it is the same as Lusternik-Schnirelmann category of this group. And in particular, if you look at the Hopf bundle of circles over S2, its topological complexity is the same as topological complexity of the circle, which is 1, as we have seen. Because this is a principal bundle, and it is special case of example 2. However, if we take this Hadel-Novid vibration, Hadel-Novid bundle, and if the dimension of the space D is odd, it is important here. So for example, if the dimension equals 3, then this topological complexity equals twice the number of robots plus the number of obstacles minus 1. So this result actually requires some cohomological computations, which I will not do. I just want to mention that if the obstacles are fixed, if the obstacles are not moving, so we're looking at configuration space of the complement RD minus M fixed obstacles, then the topological complexity of this space is 2M, and this was computed by Mark Grant, Sergei Yuzinsky, and myself. So we see that the number, if we are comparing this with the previous theorem, we see that the number of obstacles plays a role, and this, in this case, we see that the parameterized topological complexity is higher than the usual non-parameterized one. And in the special case when we have one robot and two obstacles, this parameterized TC equals 3, and the usual TC of the fiber is 2. So we see that this is actually the first example showing that the parameterized complexity is higher, or can be higher, It uses cohomological low bound. Maybe I'll skip this. I'll just skip this. So this was published in our paper with Dan Cohen and Shmuel Weinberger in Science Journal of Applied Algebra and Geometry last year. In the case when the dimension is even, the answer is slightly different. In this case, the parameterized topological complexity is 2n plus m minus 2, so it is 1 less than previously in the previous theorem. And this is proven in the paper again with Dan Cohen and Shmuel Weinberger which will appear in Annals of Mathematics and Artificial Intelligence. And I just want to mention that Mark Grant also proved this result. I think for d equals 2, he proved the same result for d equals 2, but using completely different method. I just also want to mention that we have an algorithm, a specific algorithm, which implements this idea and which is optimal in some topological sense. But in fact, this algorithm consists of dividing this configuration space on a huge number of domains, and then they are combined, and shows that they can be combined without creating discontinuities. And the number of such domains which enter this picture is at least this number which shows here, n plus m factorial square divided by m factorial, and it's a really big number. And even for n equals 5 and m equals 3, this number is already 270 million plus domains. So this means that although this topological complexity is important and it measures topological abstractions and the level of discontinuity which arises, however, the real geometric complexity is much higher. Even if we have 5 robots and m and 3 obstacles, it's already an enormous number. So my time is exactly nearly over. So I want to finish with this citation from Alexander Solzhenitsyn. So in one of his books in 1968, he wrote, "Topology, the stratosphere of human thought. In 24th century, it might just possibly be of use to somebody. But for the present," so you see that 50 years ago, topology had this image of a very abstract and remote and difficult part of science, mathematics. And people like Solzhenitsyn, very talented people, thought that it is an interesting theory, but it is remote of real life. But in fact, we see that now it's not actually. Robotics is quite dependent on topology. So I want to finish here, and I want to answer questions if there are any questions. Thank you very much.
Yeah,